glad to invite you all on the webinar of the Digital Advances in Geotechnical Data for the Infrastructure Projects. So today's speakers are going to be Richard Lowries and Farzin Hamidi. First of all, I would like to give you a brief introduction about our speaker. Richard is a customer success manager based in Christchurch, New Zealand. He is an engineering geologist with a consulting experience working on large infrastructure projects. He has assisted multiple customers to create and manage and share 3D geological models that enhance their understanding of the subsurface and support their decision making process. He specializes in product, leapfrog works, and central, which can help solve complex geological challenges and optimize the project outcomes. So on behalf of all the TAIym committee, chair, vice chair, and everyone, I would like to invite Richard and hand over the platform to him.
Thank you very much. Thank you everyone for joining us today, and thank you to the TAIym team for inviting us to come along and host a webinar. As the introduction was said, my name is Richard Lowries, and I'm an engineering geologist. Can you hear me?
Okay. Yes, we can hear you loud and clear. Uh, and I just wanted to ask you whether are you going to present first, and after that, Dr. Farzin Hamidi will do, or you're both going to do it simultaneously.
Dr. Farzin will join in about halfway through, but we can introduce him now if that works best.
Okay, so I just wanted to introduce Dr. Farzin to our audience also. So if that helps, that can be done. So Dr. Farzin Hamidi is a geotechnical engineer with nearly 10 years of experience in the fieldwork in laboratory testing, site investigation, and numerical modeling for the slope and tunnel stability. Since joining the Seequent in August 2021, he has enhanced his experience in expertise in geostudio technical support. He has contributed to various underground projects in open pit mining projects, as well as a significant infrastructure and development such as inland rail G2K, Cross River Rail Tunnel, Station Development TSD, and the Kingsford Smith Drive KSD upgrade. Farzin earned his PhD from the Geotechnical Engineering Centre at the University of the Queensland. So I request you to continue with the webinar and have a good webinar.
Thank you very much.
Thank you so much for the introduction. Over to you, Richard.
Thank you, Farzin. Thank you, everyone. And once again, I'd like to thank the TAIym committee for inviting us along to do this webinar. And we're pretty excited to chat to everyone and talk to everyone. And if anyone got any questions, please put it in the chat, and we'll get to those at the end of the webinar. So globally, unforeseen site conditions are in the top 10 reasons contributing to the cost of claims and overruns, presenting significant risk to infrastructure projects. The total value of claims in progress is $91 billion, and total extensions extend over 876 years. The hidden nature of the subsurface and the limited availability of site investigation data, combined with uncertainty of what lies between the data points we do have, is one of the key challenges facing geoprofessionals working on infrastructure projects. Not only do they need to understand the underground and identify ground risks when the limited data they have access to, but they do need to communicate this information to a wide range of different disciplines, both technical and non-technical. All of this is commonly done on tight budgets and timelines. I'm sure a lot of you across most of these unforeseen costs that occur on infrastructure projects, from seepage problems when we're doing dewatering, pile overruns, misclassified or miscategorized subgrade, unanticipated rock excavations, and maybe groundwater shallower than expected. And these are typical problems that we commonly come across when we're working on these kind of projects. So today's webinar, we're going to go through 3 sections. The first section is on existing trends. The second section is looking at some case studies that explore some of those existing trends. And the third one are digital technologies that people might want to be using or how they could be embraced. So I'm going to start with existing trends as section 1. So we're seeing trends of moving towards the adoption of digital technologies. More and more geoscientists and engineers are using technologies regularly across their projects, if that is through digital collection of site investigation information or through the production of digital drawings. This is helping to increase efficiencies across projects. It's to start with an increased trend to machine learning and generative AI. This adoption is requiring more and more people to use and manage structured data. And when we talk about structured data, we mean information that is stored in a structured way and not stored in, say, PDFs or in cross-sections or reports. So if we're looking to continue to extract as more and more insights from this information, we cannot continue to break the transfer of digital data between different parties working on projects by only providing PDF reports or only boreholes. This requires an increase in time to work on these projects, to work with this information. As more structured data is being used and captured on projects, there is a trend towards the increase of building 3D digital ground models and working from a 3D perspective, and not relying on building and constructing 2D cross sections across site and using those to communicate the ground risks to non-technical stakeholders throughout a project. And this embracement of 3D means it is becoming easier and easier for the geotechnical information to be integrated into BIM systems or BIM environments, and which in the past was always a challenge, especially as BIM was focused very much on the infrastructure and not on the geotechnical aspects of the project. I just wanted to bring up something that I think is pretty interesting. The QR code on the screen there is for the IAEG Commission 25 guidelines. So that's the International Association of Engineering, Geology and the Environment. And these guidelines were published for the development and application of engineering geological models in 2023. And there was a latest revision on the 9th of August 2024. And that QR code takes you straight to those guidelines. I wanted to talk about this because I thought that it's quite interesting to see how these guidelines have been developed as they define a framework for the development of engineering geological models. And this framework helps to manage uncertainty and integrate data. It also ensures that any of the models that we're working on remain dynamic in nature. So it means that they can be updated, utilizing continuous updates, and meaning that there's a feedback loop. And this means that there's clear documentation to be maintained throughout a project lifecycle. The guidelines also set out a process for starting from a conceptual understanding on a project, and then building, using that conceptual understanding to build a conceptual model, and through the collection of site-specific data and understanding, creating an observational model. As gaps are closed from questions arising from when we build a conceptual model and the model transitions closer to an observational model, the uncertainty on a project reduces. A key component of an observational model can be the 3D digital model. And we're going to jump into some case studies now that show how we can build a digital model and some of the value we gain from generating one based off observational data. I'm going to just quickly apologize because the first video is quite a salesy video. I don't mean it to be a salesy video. It's just got quite an interesting case study, and just quite interesting. So if it's too salesy, then I understand. But we're trying to keep this talk on a technical level. But I just wanted to raise it before I show it. But anyway, the high-speed line that is between Gelhurst and Fulda, the railway line in Germany, and it was a project that was run by Professor Quick and Colligan. It's a high-speed line that will be up to 240 kilometers per hour and will accommodate an expected 30% more passengers by 2030. 2/3 of approximately 100-kilometer investigated route. Options run in tunnels. The longest tunnel between Schultern and Micheltenbach runs a distance of 9.5 kilometers. There was over 100 boreholes explored, 15 lithological layers created, including quite a complex fault system of 88 fault blocks. I'm just going to play the video. Let me know if you can't hear it.
Richard, sorry to interrupt, but we are not able to hear the audio.
You can't hear the audio?
No,
I can hear it.
Yeah, I'm also able to hear it, Richard.
okay.
I'm also hearing it.
Cool.
You can
well, I'll play
continue
it
with it. Yeah.
and then I'll play it again, and then I will just talk through what's said on it, just for those that can't hear it. Right, so that project, for those that couldn't hear, has created a series of fault blocks along the route of the alignment. Those different colored zones that were appearing in the model itself. If I just jump into the screenshot, so these colored blocks here are representing the change in regime that's happening between the faults, and they're trying to create a model of the different material types that were happening in those fault zones. And then looking at how the behavior of that material and doing that based on laboratory testing results. This is an observational model that's built off borehole data, and they've pulled together that information into one place and built a 3D representation of the geology. This is similar to another project that we have here, and this is the Karabanki Tunnel connecting Slovenia and Austria. This is it started with an existing single tube tunnel, and that did not meet the demands for the current traffic flow. So a second tube was drilled parallel to the existing one. The length of the new tunnel was approximately 8 kilometers. This one doesn't have any sound, so I'll talk over it while it plays. This site had some very significant complex geological challenges, and we can see here in the screen in front of us that we have a complex geological map that has been generated for the project area. And what they're looking to understand on this project is some major water inflow was happening on this project, and trying to identify where that could be as part of the tunneling process. They were also looking to reduce the overbreaks, and there was a risk of methane ingress. Around 25% of the total tunnel route had a risk of high water inflow. And we can see here we're going to go from a 2D representation of the geology into a 3D geological model. This is built from a combination of data sets. So here we can see we have these big faults. This is built from the geological map and the borehole information that we can see just in the scene as part of the model. So building a representation of those fault planes to help understand where that groundwater ingress would be happening. The model was then updated throughout the process of the construction of the tunnel by also adding in some of the probe holes and adding that information in to update that 3D geological model. So the model has started from a conceptual point based on historical data, and then as more site investigation information comes in, we're starting to move towards an observational model, which is a 3D geological model. Modeling in 3D allows us to start to communicate some of the risks around the project, not just to people that are specializing in geology, but also to non-specialists as well. And then we can then use the 3D model to create 2D sections that we may want to put in a report or be used as part of construction. We can see the detail that can happen as a result of using a 3D model to generate those 2D sections that we're looking to deliver. And then communicating that in the presence of the 3D model makes it a lot easier for those purposes. So this is another tunnel project, another 3D model. This one is in Auckland. This is City Rail Link, and it's in New Zealand. It's a project by Oricon. This project is really interesting because the other two were being built during construction. This is for a different phase of the project. This is for tender. And so the client, this is for the client side, so looking to build a project or build a model that communicated the project risk to anyone that was tendering on that project. So for detail, this is a CRL project, or the City Rail Link project is a twin 3.5 kilometer long rail tunnel connecting an existing station to new stations. Also, 2 new stations were going to be added along that route. It was managed by the City Rail Link, a joint venture between Auckland City Council and central government. The project commenced in 2010 under construction via 6 contracts, and it transverses weak rock of a geological group called the Waitemata and cuts through the Pleistocene alluvial deposits and some really complex volcanic deposits as well. And so I'll just play this video, and we can see that again, this is in a built environment, and we've got the design in there and all the borehole data. This project has significantly more borehole data because it's in a central and a built environment. So we have a lot of information created from other sources. We can see all the stations and where they are along the route. The weathering along this layer changed significantly from as a result of weathering, from a UCS strength of 15 to 25 MPa. There were diverse sedimentary deposits along the route and huge challenges around soft ground conditions. We can see that here they're starting to build a hydrogeological model as well as building a 3D geological model. And one of the key benefits here, I said earlier that this model was built for the purposes of procurement, and it was really important to be able to communicate the geological conditions and the risks during the main tender works to all of the tenderers that were involved. And this was really important to try and make sure that everyone that was involved had the same understanding and that they were starting from the same point. So this model was shared with the tenderers. And we can see in this model that there is a series of, I'm just going to pop back 2 seconds. So this pink layer here is the volcanic layer, and then there's depositional events that have happened subsequently on top, and we can see each of those layers that have been deposited, which is a mix of clays and the volcanic ashes. And that becomes challenging when trying to put a tunnel through these different ground conditions. And so it was really easy to be able to communicate the risk to the tenderer around those geologies. Two more case studies. This one is a closer to India. This is an underground storage facility in India, and it's through Engineers India Limited. It's a project where an underground storage facility was being generated, and they have a large distribution of dikes across the project area, trying to understand the hydrogeological impacts on those underground facilities. And they used the 3D model to be able to communicate and understand the fracture flows that were happening on the project, and try and enhance the safety of that project and that storage facility. They also used some other tools to be able to communicate that project to a wider range of stakeholders and update any risks that are with that project. For this final case study, I'm just going to hand over to Dr. Farzin Hamidi. Farzin, are you able to take over?
Thanks, Richard. Can you hear me?
Yeah, I can hear you.
Awesome. Thanks again from Tunneling Association of India for inviting us for today's webinar. And I'm going to cover the rest of today's webinars, and hopefully we can get something out of this. So this case study that Richard kindly shared in his screen is a Seequent engineering design, which is the first residential building over a subsurface tunnel in West Bucharest in Romania. It requires an innovative solution to minimize the impact of that tunnels on the impact of that construction on that tunnel specifically. So the project involves complex geological analysis, including 2D and 3D modeling of a 1.5 meter thick raft and 37 paws, which are 1,080 millimeters diameters and 80 meters in length. So they want to ensure the safety and compliance with the strict subway operator requirements. So this is what they plan to do. So Seequent Engineering actually use Plaxis for advanced geotechnical modeling, which helps them achieve accurate and optimized design, and which leads them to the project approval within 3 months. And it reduced the displacements and the structural force on tunnel lining by 50%. And also it helps them to decide to reduce the number of building, which originally was decided to add a 10-story building to they decided to reduce it into 9 by minimizing the seismic load on tunnel. And also the reduction of a raft thickness from 2 meters to 1.5 meter, which actually saves them money. So these are all designed in this specific case study, and uh, uh, you can actually find it in this case study. Would you please go to the next slide, Richard, please? In this section, we will highlight the importance of digital technology. Next, please. File-based exchange and incompatibility or transition of a file format is still a daily issue for many engineering firms. Click next, please. Our own geoscience data report in 2021 revealed that a third of geoengineers are spending over 30% of their time managing data. That adds up to a significant impact on our productivity. But the more importantly, perhaps, is opportunity cost and devoting that time to non-value add a task in. It leaves less time for what they really matter for geotech engineer. So if you spend, let's say, 30% of your time mainly in a file transfer, so it spend less time for you to do whatever you're supposed to do. Ultimately, if you do have challenges, the risk it can open are quite significant, and the cost of getting something wrong when you could have got it right can make or break a project. That's what we actually thinking within Seequent. Next, please, slide. Ultimately, our vision is to enable more productive and streamline workflow that connect the people on the project and enable them to collaborate while delivering the pieces of the puzzle that they are responsible for. A centralized and intelligent model with dynamic change management would not only save time by automating a deliverable production and preventing rework and delay, but also mitigating the risk from early stage of design. These fit our ability to execute value engineering opportunity and so add value to infrastructure through a better understanding of a ground condition. Next, please. Seequent and Bentley driving toward the future vision by enabling core workflow to be made accessible in an off-the-shelf offering with dynamic geological modeling, cloud data management, integrated beam tunnel parametric design, and a connective analytical models. Next, please. When we start with 3D approach, it means many things click into place, such as communication and understanding. Beam and clash detection process, an analysis of a complex soil structure interaction that may present risks to be mitigated or opportunity to be taken. The subsurface digital twin, while never an exact replicate of an unforeseen ground condition, is nonetheless our best understanding, developed at significant cost and must be treated as a value asset to ensure the safety of a project. Next, please. Seequent is a Bentley subsurface company, and we are all about understanding the underground, build a better world as we collectively advance infrastructure. Next, please. So the quick overview of what we can offer within Seequent and Bentley, it is provided in this infographic map. As you can see, Seequent can offer solution from the desk study, as you can see in the lifespan of a project, until the geotechnical analysis, geotechnical modeling, and the monitoring stage of your project. Some of the products that we can offer within Seequent and Bentley, you can actually see them from the site investigation stage, which are OpenGround and Imago. And we do have geophysical packages such as AGS and OASIS Montage for doing a geophysical analysis within the site investigation data that we have available, so we can actually making more information and more insight decision. And then we can actually push them all into a 3D geological modeling tools that we have available, as Richard showed that earlier in our Leapfrog. Central is our model management tools that you can actually publish all your model and you can actually visualize them in a web browser, or you can publicly share it with your client or whoever want to see them in a web browser. So we can actually see those 3D geological model that Richard mentioned earlier. You can share them with the other team member around the globe and ask them collaborate. So it has also a version control that can help you to have a history of your project. And then once you're done in your Leapfrog model, you can actually push those Leapfrog model as a 2D section into your geotechnical analysis packages, which are Plaxis and GeoStudio, or you can actually bring the 3D geological model into Slope 3D and run the limit equilibrium stability analysis within GeoStudio. Everything that you can see in this workflow is dynamically connected. So all these products that you can see in this map are dynamically connected. It means that if you have any sort of information added into your any stage of the project, it will be automatically updated due to the implicit way of modeling in Leapfrog. So as you can see in here, it's not only the products that are working together, but also it is mainly want to show that it is cloud-based and you can actually call them wherever you want from different product, and there is a connection between these products. Next, please. So the connected workflow allows an easy transfer of data between the data, desktop, mobile, and a cloud-based software solution. For more than 5 key benefits of a connecting workflow using cloud technology, cloud storage, time efficiency, synchronization, data management, and notification. I will discuss each of these in a bit of more details in the upcoming slides. Next, please, Richard, please. So we have a data from the site investigation stage. We have OpenGround collector app. As you can see, we can actually use the collector app and we can take it on site. We can use it offline and collect our information. Once we get back to the network area, we can actually upload it in a cloud storage. And then next, please. This is our data management tools, which is a cloud. So once our site engineer upload the data, you as a office engineer, you can actually see them at the same time in a real time, what is available in that site. If you want to comment and convey the message to your site engineer, you can actually simply see it, or you can actually come to these model management tools and correct the site investigation. It has a lot of capability. You can actually report it to all these site investigation into Power BI reports, or you can actually see them in a live view in as you can see in the right screen side. You can actually see the borehole logging information, and you can actually correct them as you go. Next, please, Richard. Once you're done with your site investigation, as Richard showed you earlier, you can actually bring all the geological modeling, all those borehole information. It could be CPD data, geophysical data, or it could be a face mapping data to make your geological modeling much more flourishing and much more to update it. And then, for example, in this project, once they done the site investigation, they missed the fault zone that you can see here. By the geophysical information, they realized that there is a fault zone, so they changed the tunnel alignment accordingly in order to make this tunnel alignment much more secure. And as you can see, this geological model can be updated with the design, and you can actually add cross-section into this and export those cross-section and bring them in as a report, or you can actually do it in your subsequent geotechnical analysis and run the geotechnical analysis within GeoStudio or Plaxis. Also, as you can see, you can actually run a longitudinal cross-section, which are shown in the case study that Richard showed you earlier. Next, please. So this is a quick overview of our central. So you do have a project which has a branch ID and it has a version, and it has a quick overview of who did change to the project and what was the comments was available in this specific GeoStudy in this specific central instance. You can actually travel through the history. You can actually download the Leapfrog model, and you can actually see the comments who collaborate in this and what was the comments that are let's say done, who actually put the comments specifically in that history, in that timeline of your project. Next, please. And once you're done via your central, you do have a live connection and a dynamic connection to your geotechnical analysis package. In this case, this is the GeoStudio overview, and it's Slope 3D. You can actually see I brought the tunnel portal cross-section into this view, and you can actually see everything geological model with the same coloring brought into GeoStudio, and you can run the slope stability analysis for that tunnel portal. And if there is any specific information, you can actually see everything is updated accordingly. And you can do it both in 2D and 3D. If there is any updates, you can see it's substantially, let's say, exaggerating the geometry, it's updated. You can come back instead of doing the same project, and instead of that, you just reload it into GeoStudio. You don't need to recreate the project. Everything can be updated, and you can actually clone the analysis and run the same simulation with the updated geological model. So as you can see in this screen, all the 2D cross-section and the 3D cross-section are updated accordingly, basically based on a new information provided in Leapfrog. Next, please. So basically, as you can see here, so we already discussed the main advantage of the productivity improvement with the integrated BIM modeling, and the heart of this holistic workflow that incorporate the ground modeling with Leapfrog and geotechnical analysis with Plaxis. We would like to expand your horizon to beyond the design phase into the asset management and operation through the iTwin digital as well with the open tunneler. So next, please, Richard. So in this view, we show how the various Bentley and Seequent products fit together within the workflow. It's worth noting that the applying digital innovation in any of these areas is going to be valuable. But it is when you actually start to connect them together that you are going to get the largest benefit of this improvement. It is being able to move easily between the steps that are going to have the biggest impact of your productivity. And with that said, I will going to show you a quick video of an open tunnel designer into Plaxis. For example, as you can see here, we have an open tunnel designer, which is specifically used for designing the reinforcements. and the profile of your support system. So you can actually upgrade everything in this profile. You can import them and then update them, changing the alignment by just importing the alignment polylines, and everything, as you can see here, are possible to be changed, and all the designs and everything can be associated specifically to different chainage of this project. For example, you decided, okay, I would like to add this specific design for my portal, and the portal design of my reinforcements is differ from what I have in the middle of that chainage. So you can actually able to do it accordingly, as you can see in the view. And then once you're done with it, you can simply come back to the project and export this project accordingly. So also the other thing you are planning to do is to bring your geological modeling as well into the view. So as you can see in here, we actually bringing a different scenario for adding the cross section. So these are the cross section that are added in each specific location, so you can actually see them in view. Also, the other thing I mentioned earlier, you can bring the geological model seamlessly from your Leapfrog into Open Tunnel Designer. So this is the tunnel portal, and you can see the geological model and the support system associated with that geological model for each specific chainage. And then you can export it into a file that can be imported into Plaxis 3D, which is our geotechnical analysis tool for running a finite element deformation analysis, stress deformation analysis. As you can see, it says Python scripting code. Once you actually import it into Plaxis, it actually runs in the background, and you can see everything is imported into Plaxis 3D as you had it already in Open Tunneler. So it actually saves a lot of time. It improves the efficiency. You can do the same procedure by just importing a 2D cross section from your Open Tunneler into your Plaxis 2D. So in this case, we do have another toggle, as you can see. If you just toggle this and send it, you can simply come and import the file into your Plaxis 2D, and the code is be running in here in the background, and everything is substantially improved the workflow and efficiency in this case. You can decide if those are considered as aligning or mainly as a background information. So that's the way. Would you please move to the next slide, Richard? So with that done, I just want to finish by just providing you the location. As you can see in here, Seequent is a global company, and we have different offices. Our headquarters is in Christchurch, as you mentioned earlier, Richard. And also we do have a office in Kolkata in India. Next, please, Richard. If you want to contact us, please scan the barcodes on the left-hand side. If you want to know more about our solution, please scan the barcode on the right-hand side of the screen, and we are more than happy to help you if you need any further assistance. Without any delay, I just want to leave the floor for you guys to ask your questions. Is there any questions?
Thank you, Dr. Farzin. Thank you, Richard. And we will now move ahead with the audience for the Q&A session. So I would ask anyone from the audience, if you have any question for the Dr. Richard and Dr. Farzin, then please go ahead. So if you can see in our chat, there's a one question. It is possible to change the model parameter if linked, if possible, model parameters to cloud repository. by changing the cloud repository only.
Do you want to take that one, Farzin?
I'm trying to read that. If you link, sorry, my screen is a bit, if possible, model.
So I presume here the questions around material properties.
Yeah, that's a good question. So by just changing the material property in the cloud connection that I showed you earlier, we only have the capability to bring the geometrical and as well as material naming from Leapfrog into GeoStudio. So the material property need to be actually added after you import it into Plaxis. So, or GeoStudio. So once you import the material, you will see them as a material name. Everything is available. The properties need to be manually input once. Once you actually put those material property, so for all the project you have them. For example, you know how to do the global material property in Plaxis, you can actually bring it and transfer it from the global material. Does that answer your questions?
Do we have any more questions for the speakers?
Hi, Dr. Farzan and Richard, Rushia. So yeah, just wanted to know what is your the Seequent. It's like the Plexus and Seequent, they are all together. So what is your compatibility with other softwares like let's suppose Rock Science or any other softwares? Are you compatible with that?
Yeah, definitely.
If you want to share the data from one software to other.
Yeah, I'll start, Farzin, and then you can follow on from Plaxis and GeoStudio. So from Leapfrog, if we build our 3D geological model in Leapfrog and we start to build our conceptual understanding of the geology, that we have the ability to export 2D sections out of Leapfrog is in any position that we want as a DXF, and that DXF can then be brought into Rock Science. Seequent is all about interoperability, and we like to be able to provide people to choose the solution that they think is the most relevant for them. And so being able to generate the sections out of Leapfrog, they can be taken straight across. In terms of the 3D geometry, we can pull the 3D geometry into Rock Science as well, and that would be through OBJs, I believe. So we can generate and export OBJ formats, and that can be taken as wireframes into Rock Science. Farzin, I don't know if you want to expand on that.
That's all covered. The only thing I just want to say, we can actually import a file transfer in both GeoStudio and Plaxis if you don't want to use any other software packages. So, or if you have a third-party software, you just want to import the data into GeoStudio or Plaxis, there are possible opportunity to import them into GeoStudio. Also, if you want to have a export from GeoStudio into Plaxis, this is also doable. So you can actually export geometry. Typically, you started with a limit equilibrium quick analysis in GeoStudio, you develop the geometry. So in your detail analysis, you just want to go and do a stress deformation analysis. GeoStudio and Plaxis are talking to each other. You can actually transfer GeoStudio model into Plaxis, or you can export the Plaxis model into GeoStudio. This is the last things I want to add.
Okay, thank you. So Aditya, it's up to you now. We have another question.
Yes, we have another question from Mr. Rahul Rathod. Can tunnel modeling is done with any finite element method tool?
Okay, cool. I believe this question is related to the geometry of tunneling. Am I right?
No, I think
That's
he's asking regarding the FEM analysis. Can you do analysis and this?
so. Once we actually done with the geometry parts, the FEM analysis can be done within Plaxis. So Plaxis have also the tunnel designer tools available embedded inside Plaxis. So if you want to manually start creating a tunnel inside Plaxis, you can actually create a geometry of a tunnel and assign it into your Plaxis model. So this is also doable inside Plaxis, but the tunnel designer have much more capability, and you can import different section from it into Plaxis. That's why we actually showcase it. As I mentioned, it improved the efficiency. But once you're done with the geometry, yes, you can actually do the finite element modeling in 2D and 3D for your deformation analysis, or the, for example, actual force on your support system, bending moments of your support system. All those things are doable within finite element, which is our Plaxis. So within soil structure interaction that we have available within Plaxis, you can actually have a quick assessment of your real site information. As long as you have a data, you can actually modeling the tunnel in a finite element modeling. I hope that
So
it answers the questions, but please uh, put it in the chat box if you have a follow-up question to that. We're more than happy to answer.
so you need like a packages of softwares. It's not one software doing all the job. It's like one software making the geological sections, the other one analyzing it and all, right?
That's a good question. So you don't need to be, let's say, commit to all the packages. So the only thing we mention here is just improving the efficiency, especially in a linear infrastructure project, which you need to actually do this several times. So it helps you to improve the efficiency. You are not supposed to do it, or you're not, let's say, supposed to commit to all this. If you have it, it improves your efficiency. But if you don't, you can actually start from scratch inside Plaxis. As I mentioned, you do have an opportunity to import the borehole information into Plaxis, and Plaxis can create a 2D geometry model, lithological model, or 3D lithological model. And as I mentioned, you can actually design your tunnel profile or support system basically based on tunnel designer, which is embedded inside the Plaxis itself. But as I mentioned, the main advantage is the efficiency. And going forward, the digital modeling that we mentioned during this session. So the main highlight of this session is to highlight the effect of that in your efficiency of a project. Richard, do you want to add any comments on this?
I think you've mentioned most of what I was going to touch on. I think in terms of the 3D modeling part of the exercise, it's something that I'd be keen to understand from the audience more as well. Is anyone modeling in 3D at the moment? Is anyone developing ground models based off a wide range of data? And how, if you are, what are your experiences in doing it, and is it something that is being beneficial? And are there any challenges that you're coming across from doing it as well?
Yeah, I'm actually modeling many ground models and all, but that's if we start talking on that, the webinar will extend a lot. Yeah, because if you model the 3D in like in software like as GTS NX, so the file is so heavy that sometimes it takes 6-7 hours to actually analyze the files. So we have to come with some other solutions like making a spring model and all. So it usually saves time in that.
Mm-hmm. And is that a conceptual model, or is that an observational model based off the actual data that you're being captured as part of site investigation?
Yeah, it's like we finalize some parameters from board logs and like geology, and from lab test we go and finalize the geotechnical parameters, and then we model it in 2D and try calibrate it in 3D to see the same like 10 to 15% axial forces matching to the 2D model. Like that, we calibrate it. Yeah.
And when you're those kind of models, are they similar to the 3D models that I was showing at the beginning of the presentation in terms of a full length of the alignment, or are they small localized models
It's
around
a localized
specific
model.
challenges?
Yeah, it's a localized model. I told you, right? Making a very big model it's the software becomes quite heavy, and I just did a practical, just a small model of TBM tunnels about 100 meters in length, having two cross passages, just for learning, and it took me about um, um, 8 to 10 hours to analyze it because I had done it in great detail.
Mm-hmm. Yeah, that makes sense. How I think some of the benefits of using the kind of approaches that we were suggesting at the beginning on 3D modeling is to start to understand risk along the project, where you can then identify areas of doing those detailed models, in the smaller detailed models that then you can focus in on those parts of the design that require that additional detail. And especially if you can identify from your drilling data or from your outcrop data, or from whatever you're encountering, maybe trying to identify where the faults are going along the alignment, where you're encountering multiple faulting, or you know that there's a zone of high fracturing. Identifying those locations mean that you can then really focus in and spend more time building those models, knowing that you're doing it in the right place, and you're not spending time in an area that actually this is quite competent, and we're not just doing it for the sake of doing it. We're doing it because we know that there's a risk in this location.
Yeah. Thank you for the answer.
Does anyone else have any questions around? I'll have a go.
There's one more question from the Niranjan Kumba. In Tunnel Designer, can we change the thrust jack point in action model as a TBM selection site specific, increasing or decreasing the thrust jack number?
That's
I
a
think,
really interesting question.
yeah.
Okay, that's a really interesting question. Thank you for that. I think we'll get back to you on that question, because myself and Farzin are not experts in Tunnel Designer. I'm more a specialist in the 3D modeling of geology, and Farzin's more around the geotechnical analysis of those challenges. But if you do, we can definitely follow up with that question around Tunnel Designer.
Okay. Fine. I don't think so. We have any other questions at the moment. So once again, I would like to thank Dr. Hamid and Richard for a wonderful webinar. I'm sure that your presentation will be very useful for everyone, and I hope our members have got a clear idea on geotechnical advances in infrastructure projects. Being a design engineer, I know how difficult it is to plot the available geological data in 2D frame and interpret the geological properties. Your presentation gave a clear idea about how advanced 3D technology is and how can be efficiently it can be implemented in projects geotechnical data interpretation. I would like to inform all our past webinars are available on our YouTube channel, and this webinar will be uploaded shortly. If you are not a member and want to become one, kindly contact us for the details. Before signing off, I would like to request all the members to renew their membership for the year 2024 and ensure the timely benefits. I would also like to invite new members to be the part of TAIym, which are solely focused on bridging the experience of professional working in different projects and also act.
I think we lost him. But yeah.
I think we lost him.
Yeah. How is you are in India, right? Currently?
Yeah, Farzin and I are in India. Yeah, we were just at ARMS 13 this week. and then next week we're at iCold for the week
Okay,
as well.
big weeks, right?
Yeah.
So how is India treating you well?
Oh, it's amazing. The food is so good. Oh, it's
Yeah.
incredible.
Yeah.
So okay, like where you're staying currently? Like where you're staying in India?
In Delhi, in Connaught Place.
Okay, okay, okay. Because most of us are in Delhi, and if we can meet up, but let's see what our time permits or not.
Yeah, definitely. No,
Sure.
that'd be good.
Yeah. So yeah, we have
we've
him
met some
back.
amazing people. Oh, we have, yeah.
Sorry,
Yeah.
my
Yeah.
internet was lost and I got disconnected for a while. And once again, thank you, Dr. Farzin and Dr. Richard, for the wonderful webinar. We are glad to have you on our TAIym webinars.
Thank you.
Thank you very much.
Thank you so much for having us, and have a great rest of your night.
Yeah, and if anyone is in Delhi and wants to reach out, then Farzin and I are active on LinkedIn, so do reach out via LinkedIn, and